Here we are trying to discuss what's the logic and how a galvanometer can be converted into an ammeter. Ammeter is an electrical device used for the measurement of intensity of electric current flowing through a circuit or a device. Since current flow remains same in series, the meter has to be connected in series to the circuit or to the device where the current is supposed to be measured. Now, directly, why we can't use a galvanometer for measurement of current? There are two basic reasons why a galvanometer as such directly without any change we cannot use for measurement of current. Number one, a galvanometer has its own resistance. When already a current is flowing through a circuit, when you break the circuit to connect the galvanometer in series, due to the resistance of the galvanometer, the total resistance of the circuit increases, the current flowing through circuit will decrease. So the process of measurement leads to a decrease in current through the circuit. So the value of current decreases. That's one reason why a galvanometer as it is directly without any change we cannot use for measurement of current. The current should be same during the measurement, before the measurement, even after the measurement, if it's an ideal measurement. But here when we introduce the galvanometer for measurement, the current will decrease. When we take out the galvanometer after measurement, the current will again increase back to the previous value. So there's a change of current during the measurement. The second reason, a galvanometer is made very sensitive, highly sensitive, meaning it is used for detecting the presence of current. To detect even small current, galvanometers are made highly sensitive. So even a small current flowing through the circuit will produce full-scale diffraction in the galvanometer. Maybe 1 microampere or 1 milliampere current can produce full-scale diffraction in the galvanometer. So we cannot use a galvanometer for measurement of higher values of current. A galvanometer, one, it leads to error in the reading due to its resistance. Second one, due to high sensitivity, it cannot be used for high current measurements, only for very small current, but still there is an error because of the resistance of the galvanometer. Now, since the galvanometer has to be a low resistance device, ideal galvanometer for perfect measurement, resistance has to be 0. Then only the current will be same before, after, during the measurement. But practically no device is free from resistance. So a meter will have a resistance, no doubt. Only what we can do practically, a meter can be made a very low resistance device. So that's a practical way of a meter. Now, any device, if you connect something in series, the resistance is higher than the highest of the individual values. If you connect two resistors in parallel, the resistance is lower than the least individual. So keeping that concept in mind, if you want to reduce the resistance of a galvanometer so that the error in the reading can be reduced, you can connect a very low resistance parallel to the galvanometer so that the overall resistance of the circuit will decrease. That's the logic behind conversion of galvanometer into an ammeter. A galvanometer can be converted into an ammeter by connecting a very low resistance, we call it as shunt, parallel to the galvanometer. So the conversion part only starts from here. If it's asked for the exam, this all not demanded for writing. This all separate questions. How an ammeter is connected, why? What are the reasons behind a galvanometer why cannot be used for measurement of current? what's the resistance on ideal ammeter, or it comes in numerical questions also. Now the conversion concept starts from here. These are the basic reasons behind that. Now when you connect a low resistance parallel, the value of the load resistance is selected in such a way when the maximum current enter the ammeter, only the current needed for full scale deflection that flows to the galvanometer, the remaining current supposed to pass to the shunt resistance. So if I is the maximum current to be measured with an ammeter after conversion, before conversion the galvanometer can measure up to maximum Ig. So you make a circuit like this. This is the galvanometer. You're connecting a shunt resistance parallel to it. This galvanometer alone can measure maximum Ig, maybe say 1 ampere, but we are supposed to measure any value between 0 to 5 ampere. So just for understanding, 5 may be I. When 5 ampere current comes here, that's a maximum current through the ammeter after conversion. That time 1 ampere, which is a full scale deflection for the galvanometer, must pass through the galvanometer. So the galvanometer shows full scale deflection, and the remaining 4 ampere current passes to shunt resistance. This will join back to 5 current. So that's the maximum current we can measure. If you decrease this half to 2.5, both will decrease to half. This will be 0.5, this will be 2. So the deflection becomes half. So if you design the device for maximum current, and maximum current enter, the maximum current which produces full scale deflection passes through the galvanometer. The remaining will pass through the shunt resistance. When you reduce this half, proportionally these two will become half, the deflection also become half. Now instead of 5 ampere, if you want to measure 100 ampere, then when 100 ampere comes here, still 1 ampere should go through this. 99 ampere must pass through the shunt resistance. That means the shunt resistance must be very low compared to the galvanometer to allow 99 amperes through the shunt resistance and just 1 ampere through the galvanometer. So that's a way of designing the value of shunt resistance and totally the ammeter. This galvanometer parallel to shunt resistance is called the ammeter. Now the value has to be calculated based on the current. These two are parallel. The galvanometer and shunt resistance are parallel. So the voltage will be same for both. In voltage you can calculate as current into resistance. So I minus Ig into S will be equal to Ig into G. From this you can find S as Ig into G by I minus Ig. Now this is the value of shunt resistance. It's very clear. Ig and G are constant for a given galvanometer. The maximum current which can produce full scale deflection and the resistance of galvanometer both remains constant. So when I increases, the denominator increases, the shunt resistance will decrease. Like as we told, 100 ampere, this has to be very low resistance. G represents the resistance of the galvanometer. Now these two together becomes an ammeter. The resistance of the ammeter, since these two are parallel, we can calculate as 1 by Ra is equal to 1 by S plus 1 by G, taking LCM, G plus S by SG, taking the reciprocal. So Ra equal to Gs by G plus S. So this is the logic and the formulas behind conversion of galvanometer into an ammeter. In this particular section is known as the ammeter. Practically, when we see ammeter in the lab, we never see the shunt resistance that will be inside the box. We only see the galvanometer part, which shows the difference.